We're on number 4 now? The fourth one, segment? Okay. Okay, so in this step on the dependent sources step, you want to write the controlling quantities in terms of the node voltages in this case. So here's a controlling quantity V2. Okay, so I need to start writing some equations. So what you need to do is you need to go to where V2 is. V2, here's V2. Can I write this in terms of my node voltages? Now remember, my node voltages are VA, VB, VC, and VD. Those are the only node voltages I have in this problem, 4 of them. Can I write V2 in terms of one of those? Yeah, easy. Easy peasy, right? V2 is just equal to VA. In fact, I said it earlier. Or no, I didn't. I said V2 is equal to VOC. So V2 is equal to VA. So we've done that step for this dependent source. Now we have to do it for this dependent source. Okay, so the controlling quantity here is I1. So we got to go and look, where's I1? Oh, here's I1. Can I write that in terms of the node voltages? Yeah. Yeah, it's just going to be VD minus VC over 2K. Okay, so great. So VD minus VC over 2K. All right, I'm done with that step now. Oh, I just realized something. Here I said, to get VOC, I will use this picture with node voltage analysis. But how am I going to get VOC? Where is VOC? What's the definition of VOC? It's the voltage at the terminals when the terminals are open. So I should have identified it. It's very important to identify it, because otherwise I'm looking for something and I don't even know where it is. Now I know where it is. So don't forget to do that. Okay, so it looks like V2 is equal to VA. It also happens to equal what we're looking for, VOC. So as soon as I find the node voltage VA, I'm done with this part of the problem. Okay, so I have finished the step about the dependent sources because I only had 2 dependent sources and I fulfilled what I needed to do for each of them, which was to look at the controlling quantities and come up with an equation to write those controlling quantities in terms of the node voltages. So I'm done with that step. Supernodes. Okay, has anybody been reading the forums on the online course? Because there was a question that came up about supernodes. You should read them. They might actually help you. It was somebody named Siv. And so they were trying to figure out, how, what's a supernode? And I said, well, from your vocabulary list, if you had memorized your vocabulary, it's very, very simple. A supernode is merely any voltage source and the nodes on either side. That's it. So we've got 2 of them here. Here's anytime there's a voltage source. Okay, so here's a voltage source. Okay, this is the reference node. I'll just repeat it here instead of just making this one big black dot. But you all know this is all just one node here, right? So this is a supernode right here. So I'll just draw a little circle around it. And then I've got another one. Because even a dependent voltage source, still that makes a supernode. So there's another supernode. So I've got 2 supernodes here. So that's great. You identify the supernodes, but you're not finished with that step. Because in addition to identifying these 2 supernodes, you need to write equations for each one of them. And the equation that you write is, you have to write, it's kind of similar to what we did for the dependent sources. You write the controlling quantity in terms of the node voltages. Same idea here. You take the voltage of the source that you made the supernode out of, and you put it in terms of the node voltages on either side. So in this case, 2 millivolts is equal to VD minus 0, or just VD. Okay, so that's what we got from this supernode. And then this supernode tells me that V2 over 5,000 is equal to VC minus 0. I'll show the minus zeros. Okay, so that's what you have to do in this step. You identify the supernodes, and then once you identify the supernode for each node, you write the equation that gives the voltage of the source in terms of the voltages on either side. So that's where I got the 2MV is equal to VD, and then V2 over 5,000 is equal to VC minus 0. All right, so that's that step. And then the final step, since this is node voltage analysis, it's Kirchhoff's current laws. So we want to write Kirchhoff's current law for every non-reference node. So let me count. How many non-reference nodes do I have? One. It's just one. Right? Because now this is a super node, but part of it is the reference node. So you don't write Kirchhoff's current law there. We're not going to write it here. Really, the only node that we need to write Kirchhoff's current law for is node A. So please don't forget to tell me what you're doing. So tell me, you're doing Kirchhoff's current law at node A. Okay. Because it's the only node that's not a reference node. Because now that we've got these two things as supernodes, they're part of the reference. So you don't do Kirchhoff's current law there. By the way, in the forum discussion, one thing that I said, which I'm not sure was, it's a really good thing to say, I'm just not sure that it was totally clear. I want to make sure it's clear. For the purpose of step 4 here, the supernode step, you do kind of have to look inside the circle and see what's going on, because you have to look at the voltage of the source, and then you write it in terms of the voltages on either, the node voltages on either side. So for that step, the node, that supernode, you have to look inside it. It's transparent. But for the purpose of step 5, where you're doing Kirchhoff's current law, that node really becomes like a big black dot. You don't have to look inside of it. You're just drawing Kirchhoff's current law. I mean, you're going to apply Kirchhoff's current law. So if you think about these as two big black dots, they're both part of the reference node. So really, this is the only non-reference node in the problem left. So that's the only node that I need to do Kirchhoff's current law. So that's not so hard. Let's see, Kirchhoff's current law. We've got 100 I1 plus VA over 20K, right? Tell me if you're not following how I'm getting these. And that's it, equals 0. Yes? Pardon?
Minus or plus?
Well, I1, okay, so I'm taking currents, this, I always do it this way. I always take currents leaving the node as positive. I know some people always take it the other way, but okay, so if you had done that, then I would have had to do this, but then that would have been negative too. And it's still the same equation. So I just had it both positive. Okay, so there's my equation, Kirchhoff's current law at node A. And I feel like I'm done with this problem. You know why? I have, let's see. Okay. If I substitute what I found I1 is in terms of node voltages, substitute that here, right? This equation now only has node voltages. So that's one equation with just node voltages. Here's another equation with node voltages. Here's a third equation with just node voltages. And I'm sorry, V2 is not a node voltage, but we know that V2 is equal to VA. So now it is. And look, the unknowns are VA, VC, and VD. The reason VB is not unknown is because we know it's 0. So really there's only 3 unknowns in this problem. I have 3 equations. 3 equations in 3 unknowns. And just to be clear, the unknowns are VA, VC, and VD. Pardon? Yeah, VD is not even an unknown. So yeah, anyways. But you need VD for anyway. You've got the right number of unknowns, the right number of equations. Do I want you to do that algebra on the test? Am I going to check your algebra? I'm not. Do not waste your time doing algebra that you are going to make a silly mistake and get the wrong answer anyway. That's not what I'm testing for. I know you know math. I know you know how to solve n equations and n unknowns. So if you just tell me you have 3 equations and 3 unknowns, and one of the unknowns is exactly what you're looking for, VA, because VA is equal to VOC, and that's what we were looking for, you're done. Okay, so I feel done, and really, I didn't even write that much. I know I erased some of it, but even so, I didn't really write that much, but it was clear, it was methodical. I'm not done with the problem yet, because I'm only halfway through, right? To get the Thevenin equivalent circuit, because I need VOC and RT, I've only done half of it, right? I got the VOC part. I still have to get the RT. And we talked about the fact that RT was equal to VOC over IC. So really, the only thing left to do is get ISC. So, and of course, you would just use more paper, right? You're not going to erase. So on a new sheet of paper, it maybe, or at least on the blank part of the bottom of the piece of paper that you're using, put something like, okay, now, once we have, and say we have VOC, especially if you don't actually go through the math and get the answer for VOC, tell me that, okay, you know that you can get it. You're not going to actually take the time to do it, but you can get it. We have VOC, now we need ISC. So the question is, how are we going to get ISC? We need to draw a new picture. Because the definition of ISC is you go to the original circuit and you shut it out. Short circuit it. Okay, pause.